So I want to talk about effect from theory of functions, but do not afraid. You'll see soon that it's closely connected with some problems of additive combinatorics and Hamilton theory. So about theory of functions. We have a function on torus, and of course we can consider Fourier transform of this function defined usual way. And after that we consider the following norm. The following very nice norm A of t. It's called also linear norm. It's just L1 norm of Fourier transform of my function f. So that is the following sum. After that, take a space of functions f having finite norm, finite linear norm, and it's very nice fact that this space is just an example of Beurling algebra in the sense that if we have two functions, then the norm of the pointwise product of these functions, ordinary product of this function, does exceed the product of the norms of these functions. So that is a Beurling algebra, and there is a nice result of Beurling-Helson, which say the following. Suppose that we have a sequence of functions e to the I and phi is any continuous map of torus. And suppose that this sequence of functions have bounded norm. Then my function phi is just a linear function, mu t plus something. It's a very surprising result. Having some quantitative estimates, we derive some structure on the function phi. And also, this theorem has a nice consequence. We can describe all endomorphisms of this algebra. All such endomorphisms are trivial in the sense that there are just linear endomorphisms of this algebra. So it's a nice fact, but Jean-Paul Gahan in ICM in 1962 conjectured that a more strong result takes place. Suppose that our norms grows like small of log of n. Then this weak condition would imply that phi is a linear function. It's easy to see that if this conjecture takes place, then it's sharp, because if I take a piecewise linear function which is not linear, then these norms grows like log of n. It's not really a deep result actually. But this conjecture looks very interesting. The first quantitative result in the direction was obtained by Lebedev, who proved that if I have more or less double log growth here in some power, then this weak condition implies that phi is a linear function. Our main result is the following. If we have log of n in some power here, then it would be enough to have a linear function. Lebedev theorem uses an interesting result from additive combinatorics, and we also apply another tools from additive combinatorics and Hamilton theorem. So let me say a few words about the proof of Lebedev. It's first, and after that about our method. So the main idea of Lebedev was discretization. Instead of continuous problem, we consider a discrete one. So let us take a restriction of phi onto discrete totals, Z10, that is just considering these values of phi. We have a new function phi star. And from a general result on the restriction, it's easy to see that the Wiener norm of our new sequence e to the I and phi star doesn't exceed Wiener norm of the previous function. And here I talk about Wiener norm on the n in the sense that in the n we consider the following discrete transform of the function f. So instead of considering continuous function, we take a function on the n. Okay. Moreover, we can approximate all these numbers phi star by rationals with the same denominator q using ordinary Dirichlet theorem, and we need in the accuracy 1n by Lebedev method. So Dirichlet theorem says that we can approximate such numbers if we take q doesn't exceed n to the n. After that, Lebedev proved the following main lemma. To formulate this lemma, I need in quantitative theta of m, that is not just norms of functions e to the I and phi, but maximum of the first m function. Not m, but 2m plus 1. It's not important. It's important that these functions are growing. So, the main lemma of Lebedev says that suppose that we have approximate our numbers phi star of x by rationals with the common denominator q and with the accuracy 1 over n, then there is a connection between theta of q and this guy. After that, we apply Dirichlet theorem taking q equals n to the n and solve this inequality in terms of theta. Then we obtain that theta can be taken double log, and we obtain a contradiction immediately. So this inequality provides us a double logarithm bound. I should say that our main advantage here is just taking smaller q, so finding better approximation than usual Dirichlet theorem gives us. So to obtain this main lemma, Lebedev used some results from additive combinatorics, more precisely Littlewood conjecture in the ZP. So let my n now is just a prime number, p. Then there is a result on Wiener norms of characteristic functions of Cn, which was proved by Konyagin, and actually we used a result of Sanders, a modified result of Sanders. So this theorem asserts that if you have a set S of large density, so very huge subset of CP, then Wiener norm of this function, of the characteristic function of S, is at least this quantity. So even in the case of finding theta of, say, theta of size 1/2, we have square root of p over something, PZP. So it says that basically Littlewood conjecture in ZP hasn't solved yet, because we know in Z there is log bound for Wiener norm of the characteristic function. And in the PV, we have just square root of log minus epsilon, and that's the equation. But that's the partial result in the direction, and we can consider such type of theorems from another perspective. So suppose that we have a set in the P with really small Wiener norm of size, say, log of very, very small sets. Then this theorem says that it can be so if the density of set is small. So, quickly speaking, if Wiener norm is small, then the only possibility for set to have small Wiener norm is to be small. So that's another interpretation of this result. Okay. So that's the scheme of the proof of Lebedev-Lemma. We approximate our numbers by rational with the common denominator, and after that use some calculation. So the first identity is a trivial because the absolute value of e to the I and phi prime is just 1. So this is trivial. That is possible identity. And that is Hurley. The first multiple is just our Wiener norm because that is L1 norm of Fourier transform. And the second multiple is L4 norm of Fourier transform, which is called in additive commutator's daily differential. So that is very nice quantity. So because of we know that Wiener norm is small, it means that this guy is large. So the energy of some object are large. Moreover, we can sum this equality onto n from 1 to q, and after that we quickly obtain the interpretation of this inequality in terms of my function phi prime and some quadruples. So this inequality says that there are a lot of quadruples x plus y equals z plus w, which are called additive quadruples, such that phi prime of x plus equals this. So there's a very good sign here, because if we are trying, what we are doing, we are trying to prove that our function phi is linear. But if it's really linear, then the second inequality is just a consequence of the first one. If phi is linear, then the first inequality applies the second. But this inequality says that, of course, phi is not linear yet, but there are a huge proportion of additive quadruples where phi looks like linear function. That's a good sign. After that, I finish the proof of Lebedev quickly. After that, of course, I can take w like x plus y minus z, consider this function, and after that I interpret this inequality like a lower bound for the zero set of my function. So this function of 3 variables has a lot of zeros. The final step, I project my phi onto 2 dimensions, obtaining one-dimensional set with the same measure. So I take a huge projection of this set of 0, and my projection, on the other hand, my projection has a huge measure, but on the other hand, the projections can be expressed in terms of phi prime, and it can be proved that this projection has small Wiener measure. But we know that large sets cannot have small measure. So that's a contradiction, and it gives us Lebedev's inequality. So what's about our method? We insert just one new conception in this proof. It's conception of the additive dimension of a set, and to define this notion, I need in the definition of dissociated sets. So, very general, if you have an abelian group, then a set lambda is called dissociated if any equality of this form, where epsilon are just plus minus ones, imply that all these epsilons are 0. So it means that my lambda has no short relations between its elements, like x plus y equals z. So, for example, if we take f2 to the n, then lambda is dissociated if and only if lambda is a basis of f2 to the n. So it's some additive analog of a basis. Okay. So after that, a set S has dimension, the dimension of a subset of an abelian group. It's just the size of a maximal subset of this set S. So just the number of elements of its basis, roughly speaking. So, and after that, we obtain our main lemma. Surprisingly, but sets with small Wiener norm have really small dimension. So if we have this norm, the dimension is bounded by this one. And it gives us a new information about the elements of my set S with small Wiener norm. By the definition, any element of my set S can be represented as a sum with plus minus ones of this lambda set, of this basis set, by definition, by the maximality of lambda. And the sum is small, because it's just number of elements in lambda. So, more or less, sets with small Wiener norm, it can be very huge, but it has really small dimension, and I have this representation for any element of S. After that, our arguments are very natural, and we obtain an improvement immediately. Instead of using Dirichlet's theorem for the whole set S, we just approximate our elements of basis with this accuracy. Then, by the triangle inequality, just by a triangle inequality, we can approximate all elements of S because of this. Okay? And to obtain this accuracy 1 over n, I need in Q of size this one, because I use Dirichlet's theorem to sets of lambda, not to sets of two elements of S. And lambda has size k squared, so that is something like k to the S, and k is, I recall you that k is just Wiener norm, which is small, that is just some logarithms. So we replace this n by some logarithm, and it means that we win a logarithm. That's all. But how to prove this main lemma? So we obtain the following lemma on additive relations between elements of any subset of S. You see, it's very natural that there are a lot of solutions of such types of equations in the whole S. It's more or less Leibniz's argument, but actually the same holds for any subset of S. Any relatively large subset of S has a lot of solutions of this equation. This quantity is also called TK. Okay? So if we have this lemma, after that the proof is very quickly. Just apply our lemma to the set of lambda, that is our basis. So from the one hand, the number of solutions of this equation is at least this guy, that just what the statement of the previous result, right? Of the previous lemma. On the other hand, our lambda is a basis, so there are no short relations between elements of lambda. So it means all these relations are trivial. It means that this sequence is just a permutation of the left-hand side sequence. And more or less it means that the number of solutions of this equation is lambda to the k times k factorial, but actually I should write c k to the k. Here it has the same rate of growing. It's not important. And after that, optimizing over parameter k, I obtain the required bounds for lambda. And also, we need in this key, so it means that actually we do not need in the full power of dissociativity of lambda, we just need to count the number of solutions of exactly this equation. What it means. So actually I didn't say you how to use function phi in these arguments. So truly speaking, I need to modify the arguments to involve phi in it. So the real definition 1 is the first approximation to the required notion. Is the following. We consider a more difficult family of dissociated sets, so we just replace plus minus 1 by some bounded numbers, and moreover we just consider finite really short relations between elements of lambda. Because of here we need in just such of case. And it allows us to win one more logarithm here to replace lambda by a logarithm of lambda, because of k has size more or less logarithm of lambda. Of course, for this type of sets, we need to reprove our upper bound for tk of lambda, but it can be done. The proof is combinatorial. So you see, if maximum is attained on this term, we have a gain down to the k, k to the k. But actually, we need in the definition which involves phi. So the real notion is the following. We do not need just in inequalities, but also the definition was in inequality here. So if this equality and this inequality take place, then O as I are equal to 0. After that, we should redefine our notion for decay. That is just number of solutions with this equality plus this inequality. Prove an analog of the previous upper bound for decay and use the previous arguments. Okay. So, surprisingly, these arguments about the dimension of sets with small linear norm allows us to say something non-trivial about the original Littlewood conjecture. Our first result in the direction is the following. Suppose that we have a set S in ZP, a really small set, then a full analog of Littlewood conjecture for such small sets takes place. The proof is very simple. We know that the dimension of such small sets are small, so using Shkredov theorem we can approximate all elements of the basis of S and has all elements of S, of the original set S. And after that, it means that there is some Q such that Q times S lives in really small interval, say from P over 10 to P over 10. This subset of ZP has more or less the same behavior as a subset of the integers, and it means that we can apply the original Littlewood result of Konyagin to this set, the original result of Konyagin is Z, to this set. So it gives us this theorem. So for small set there is no any problems with this Littlewood conjecture. For large sets we have an ugly result a little bit. It says that if my set S is really large, then I can say something non-trivial on its linear norm, and if we rewrite this ugly lower bounds, then they say that for small s there is no any problem, but also for very huge s of this density, we also has a non-trivial bound in Littlewood conjecture. The initial question here, what about the sets of medium size? It's turned out that another instruments from additive converters can be applied in these situations, and that's all in progress. Thank you for your attention.
Any questions?
Yeah, so I think in the theorem of Beurling-Helson, the conclusion is that phi is...
Theorem what?
In the theorem of Beurling-Helson, the conclusion is that phi is affine, right? And the leading coefficient mu is an integer.
Yes.
And can you expect the same thing for the conjecture of Kahn, namely the fact that the leading coefficient will be an integer? Because it's not any... your function is from mu t plus phi of 0. And u is an integer.
Yes.
In the conjecture of Kahn.
No. I mean, by linear function, I meant exactly the same. That nu of t equals phi of t equals nu of t plus constant, where nu is an integer.
That's how you. Okay, that's how you do it.
Yes. Sorry.
Any other questions? If not, let's thank all three speakers of the late morning session.